So in the earlier video, we learned that ionic compounds were formed from atoms that formed ions, which are positively charged atoms. And the compounds are formed when positive and negatively charged atoms come together and they have an attraction for each other. All right. So even though the compounds are made up of these positively and negatively charged atoms, the overall compound that they make is always going to be neutral. All right, so let's see an example of that. All right, so this is easy to see if you're thinking about something like sodium chloride. All right, so if you have sodium, that makes positively charged ions, and chloride or chlorine makes a -1 charge. All right, so this guy is +1, this guy is -1, but notice this is overall neutral, because a +1 exactly cancels out a -1. All right, but sometimes things can combine in other ratios in order to achieve that neutrality. All right, so the question is, let's say that we had calcium ions, and if you look at the periodic table, you could see that it's in the position where it would want to make +2 ions. And you also had fluorine. All right, and when fluorine makes an ion, it's -1. All right, so how could these atoms combine to make an overall neutral compound? All right, and the answer is that they don't combine in a 1-to-1 ratio. All right, you would actually have to have more of the fluorines to balance out that charge. So when they make a compound, it's going to be like this, where you're going to have 2 of the fluoride ions for every 1 of the calcium ions. All right, and we're not doing formulas in this unit, but I'm just going to go ahead and mention the formula for this right here is something that you guys probably have seen before, NaCl. And notice that when you're doing the formula of the ionic compound, you don't put the charges on the atoms. All right, even though in the actual compound there are charges on those atoms, when you're drawing the formula, you don't do that. All right, and the reason for that is that the overall compound is neutral. All right, so for this right here, we have 1 calcium and 2 fluorine atoms. So the formula for that is going to be CaF2. All right, so notice whenever you have in a formula, whenever there's only 1 atom, you don't put the 1. All right, so another way to think about the way that the ratios would form would be to think about the required ratio that would be required if you had a transaction from the neutral atoms. All right, so what I mean by that is, let's pretend that we had calcium, neutral calcium. All right, so let's say that you had neutral calcium atoms and neutral fluorine atoms. All right, well, what would these guys want to do? All right, calcium, in order for it to be stable, it would say, I want to lose 2 electrons. All right, fluorine, in order to be stable, wants to say, I want to gain 1 electron. All right, so how would these guys, essentially conduct a transaction? Well, this guy wants to lose 2, this guy wants to gain 1. So not everybody can get what they want if it's a 1-to-1 ratio. But if you had an additional neutral fluorine, which also wants to gain an electron, essentially what's going to happen is calcium could give 1 electron to this fluorine and 1 electron to that fluorine. All right, and then everyone gets what they want, and that after that happens, that ends up making calcium +2 and fluorine minus. All right, notice you end up getting the same thing regardless of the way you think about it. You can think about it as, what ratio of these ions do I need to have to combine, or what ratio of these neutral atoms would I need to have this, along with the transaction of the electrons. So luckily, when you need to think about the ratio that's required in order for atoms to combine to make ionic compounds, there's a little bit of a shortcut to figuring it out. And it goes by a couple of different names. One is called the crisscross method. Another is called drop and swap. All right, but both are basically the same method. All right, so the way this works, first of all, you're going to write the symbols for the ions side by side. All right, so I'm going to write calcium +2, and I'm going to write fluorine minus. All right, so what you're going to do then is you're going to either mark out or ignore the sign of the charge. All right, so I'm going to pretend, so first of all, when it says minus, remember what that means is -1. All right, so what I'm going to do here is I'm just going to say let's ignore that positive and let's ignore that negative right there. And then what we're going to do is crisscross the numbers. All right, and this is what they mean by, the drop means the drop the sign, and then swap is swap the numbers. All right, so we're going to take this number right here and we're going to put it down right there. Take that number, put it down right there. And when you do that, it's going to give you Ca1F2. All right. And so the last thing that you're going to do is simplify the formulas by reducing, either removing any ones in the formula or simplifying to a simpler ratio. So for example, we don't put ones in formulas. So this becomes CaF2. All right. So what do I mean by simpler ratio? All right, well, let's pretend that we are doing this for magnesium, which has got a +2 charge, and oxygen, which has got as an ion, has a -2 charge. All right, we could do the same thing. All right, let's drop the charges and then swap the numbers, all right, or crisscross them. All right, and that gives you Mg2O2. All right. Well, the thing is, what this is saying is that you have a ratio. You need a ratio of 2 magnesiums for every 2 oxygens. Well, just like with fractions, that's the same thing as saying you have a 1-to-1 ratio. So this gets converted to Mg1O1, which eventually would get converted to just plain old. Well, I'll do it in steps, which would get converted to MgO. All right, so moving on. So when you look at some of the formulas of compounds that we've shown so far, things like sodium chloride, which we said is made up of a 1-to-1 ratio of a positively charged sodium ion and a negatively charged chlorine ion, you might think that if you had like a crystal of sodium chloride, for example, that you have these individual units of 1-to-1. All right, so that would be a unit of sodium chloride right there, and this would be a unit of sodium chloride right here. But this is actually not what you would have, all right, when you have sodium chloride. What you actually have is a 3-dimensional arrangement of continually repeating units of the ratio in that formula. All right, so what do I mean by that? This is just a little representation of what like you would have in a crystal of table salt. All right, this is a 2-dimensional arrangement of it. But if you take a look at this, what we have is an alternating pattern of positively charged ions and negatively charged ions. All right, the positively charged are called cations. The negative ones are called anions. All right, so and if you can think about this, this would keep on repeating. So what would be right here? See if you can predict what would be right there. All right, that would be a chlorine or chloride ion, and down here you would have a sodium ion. All right, and notice this arrangement is very sticky. This chlorine right here, you notice that it's got 2 sodium neighbors. This sodium has got 3 chlorine neighbors around it. All right, but the thing is, this is drawn 2-dimensionally. What you would actually have is a three-dimensional arrangement. And this little graphic right here shows an example of that. So this notice that no matter which way you go, if you're going up, it alternates purple, green, purple, green. All right, if you're going back, you get that same arrangement. And if you go this way, you have that same alternating structure. All right, so the name for this 3D arrangement right here is what's called a crystal lattice. All right. So this right here shows an example of a crystal lattice for something that has a 1-to-1 ratio. All right, so this right here might be an example of, say, NaCl. Like literally, take the smallest, take a grain of table salt and hit it with a hammer. All right, and take the smallest speck. All right, even this would be this would be too small for your eyes to see. But those things are just arrangements of atoms just like this. They would just go probably for millions of atoms in each direction, all right, because the atoms are so small, but they still have that alternating pattern, all right? So that is a 1, and you can tell this is a 1-to-1 arrangement of cations to anions. All right, and just a little vocabulary. One way to remember this is to think, when you think cations, think Ca, and when you draw the T, draw it like a big plus. All right, so that will help you to remember that is a positive ion. All right, in anion, think A negative ion. All right, and so those are the terms that you have for that. But this could be sodium chloride, but it could also be something like sodium fluoride, which would also have that 1-to-1 ratio. All right. So a couple of physical properties that you're going to tend to see in ionic compounds. One thing that all ionic compounds tend to have is that they tend to have very high melting points. All right. It is really, really hard to melt an ionic compound. So think about trying to melt table salt. All right. If you put table salt in a stove and put it on the stove, you could sit there all day long. It's not going to melt. All right. It is very, very difficult to get it to melt. All right. I'm actually going to post a video showing someone melting it. It can be done, but not with normal equipment. All right. The reason for that, all right, remember how these ions are connected to each other. All right. And up here, you see the crystal lattice. All right. These things, every positive thing in this is surrounded entirely by negative things and vice versa. All right. So all of these atoms are really well stuck to each other, so nothing can slide past each other very well. All right. And that leads to a very high melting point. All right. The next property. So another property that ionic compounds have is that they tend, at least when they're in their solid form, they tend to break into neatly organized shapes. All right. This can be explained when you look at the pattern of how the atoms are arranged. All right. So let's pretend that you had this arrangement of positively and negatively charged ions. All right. So if you take a look at this, what if we were to compare this top layer of it right here to this bottom layer right here, and just say, would this be an attractive interaction or repulsive? All right. Well, notice right across from everything positive is something negative. So it would be a very attractive relationship between this top layer of the top layer right here and the bottom layer right here. All right. But let's say that we were to take this magical hammer, all right, and we're just going to give this thing a whack right there on this bottom layer. All right. Well, what that's going to do is that would want to shift this bottom layer over a little bit. And if you think about what happens in that process, it's going to move. Actually, I got to draw in one more. I got to put in a negative ion right there. All right. But it's going to shift everything over, and then all of a sudden you have negative right across from negative, positive right across from positive, and this suddenly becomes a very repulsive relationship between the top layer